Okay, so here's our next video all about trying to get the value of G from our pendulum experiment. So what we've been doing so far is looking at the variation of the average period, that's this column here, with the length, that's our independent variable. And we plotted a graph and we calculated delta t, and we're just going to keep this here for now, but we're going to do something slightly different in order to get that value of G. As you hopefully will have picked up, in order to get G, or in order to really analyze this experiment, what we need to be doing is manipulating our data. And specifically, what we want to do is plot, instead of T average, we want to plot T squared. Okay, that's because the equation to do with the pendulum has a T squared in it. So what I'm just going to do is going to put my label up here. I'm going to put the unit just so I'm making sure I'm keeping track of it. There we go. Okay, T squared gives second squared. And this is why Excel or using any kind of spreadsheet is useful. We can just stick in that value and then square it. Power of 2, if I did that, would be power of 3, power of 4, etc. We're going square. Notice we've got 0.43. You could check that with a calculator. I hope it's correct. We're going to copy and we're going to paste that in. We've got our values in there again. We're going to do exactly the same thing. Whoops. We're going to select our data, press Control, select the second data, press Insert, and then go to Scatter, and we've got that there. I'm aware, by the way, that I'm doing this quickly. I've done this quite a number of times. It's not the first time I've tried to shoot this video, to be honest. So do take time just to familiarize yourself with those little shortcuts. Controlling, pasting, selecting data is all really, really important when you're using Excel to make it an efficient process. Here's our graph. It looks pretty good. Nice straight line. Okay, we can confirm that by adding a trend line. This time we are going to go linear, and we're going to display our equation on the chart. Okay, very good. Now, as I sort of mentioned in a previous video, and way of checking that our trend line is a good one, is to have a look at the R squared. That's a good value. R squared is 0.9971. It's a statistical analysis. It sort of tells us basically how far the points are from the line. And if that number is 1, then they are very close to the line, or if not on the line. So here 0.9971 is very good. All right. Now, why is this important? We've got a gradient value for our line, and that's the bit that we're really, really interested in here. Now, to move on, I'm just going to switch to our presentation. We'll have a look at the graph. This is the graph that you've just seen on the screen there. Okay, we've got our equation on there. And what we're going to do is a little bit of a comparison. Hopefully, you'll be familiar with straight lines. Y is equal to mx plus c. Now, you may use different notation, ax plus b, kx plus b. There's various different ways, but the way I will be using is mx plus c. Y, obviously the y on the y-axis, x, the x-axis. Then we've got m, which is the gradient, and c, which is the y-intercept. So in this case, we have an equation which is equal to y equal to 3.9345 plus this number here, which is the y-intercept. Notice I'm using a lot of significant figures. I wouldn't normally work this heavily in significant figures, but I'm doing so just now, so bear with me. Now, why are we doing this? You'll notice that our equation for the relationship between t squared and L is given in this way. T squared is equal to 4 pi squared L over G. Now, what was missing from the original version of the equation is probably this 0. I've just put this 0 in there so that we can compare. Hopefully you can see by the colors I've used is that for everything in that y equal mx plus c, that straight line equation, we can compare it to one from our formula that we've been given. So in this case, y is just t squared. That's what we're plotting on the y-axis. L is just x, because that's what we're plotting on the x-axis. 0, well, according to the theory, the intercept, c, should be 0. But actually what we find in our experiment is that it's not quite 0. It's very close to 0, 0.0295. Not bad. We'll be happy with that. Now, why are we doing this? Well, big step there is that it must be the case that everything in black is equal. So 4 pi squared over g must be equal to the gradient. And the gradient is something that we know. We know the value of the gradient, 3.9345. We can then use that to calculate a value of G, simply by swapping those. If m is equal to 4 pi squared over G, then G is equal to 4 pi squared over m, and that gives me a number of 10.032 meters per second squared. Okay, pretty close to the value of G. I'm quite happy with my made up numbers. What I'd like you to do just now is try all those steps yourself. Okay, what you're going to do is you are going to plot your graph of t squared. You're going to fit a straight line, and you're going to find the gradient. And then you're going to use that gradient to calculate the value of G. And what I'd encourage you to do at this stage is probably pause the video, because we're going to do a bit more analysis after that. So I'm hoping if you're still watching, you've got a value of G from your data analysis. The bit that remains is to kind of just do the last point, which is to think about the uncertainty in G. Now, this is a bit tricky and involves a bit of work, so I'm just going to show you how to do this just now. Okay, now, the way to do this is we're going to go back to our spreadsheet, okay, and we're going to use one more function. We've got a function which is, I think, short for line statistics. Okay, other people out there will know better, so tell me. Line statistics is something which will tell us the statistics of our straight line that we're fitting. And the way we do this, we've got to be a bit careful. We type line st, open the brackets, and then we select anything that's on the y-axis. We comma, then we select the numbers on the x-axis, and then we have to input an argument. Oops, true, true. Don't worry about what these mean. I'll be honest with you, I don't really know what they mean myself. Okay, what that returns to you is a lovely table. Okay, full of numbers, excellent for us to do some analysis with. Now you'll notice, hopefully there, that we've got some numbers that we recognize. Okay, we've got 3.9345. Well, that's actually our gradient. We've got 0.29, essentially 5, that's our y-intercept. Then we have two numbers below them. This here, well, this is the uncertainty in the gradient. This here is the uncertainty in the y-intercept. So this is just a statistical way of doing this, right? Excel has provided this for us. There are other ways of doing this, which we'll discuss later, but to get the uncertainty in your gradient, you can simply read it off Excel. Excel does the work for you. So we'll just come back to our presentation. Okay, there's that table again. I've just cut that from my Excel spreadsheet. And really, we're going to work with this one here. This is all about our gradient there. Gradient there is 3.934505. And the uncertainty in that gradient, so basically how unsure we are of that gradient, is 0.106. Okay, the blue boxes that are highlighted there, I'll remind you, those are for the y-intercept. So it might be in your experiment, you might want to do some analysis of the y-intercept. Well, you can get your y-intercept value, and you can also get your uncertainty. It's quite a big uncertainty there. It's actually over 100%. So that's kind of interesting and worth looking at. Now, why are we doing this? Here's the big finale. Well, we know the gradient of our graph is like this. So we can write it now with its uncertainty. We've got 3.934505 plus minus some number. Okay, and that's at 0.029499. I've said before, I'm working to a lot of significant figures here. Okay, another way of writing this, and the way that it really should be presented, is as follows on the screen: 3.93 plus minus 0.3. Notice we give the uncertainty to one significant figure and then kind of work backwards so that it matches the number that we've got there. Okay, I've just noticed I've missed a 0.0 there. Okay, my apologies. So, why are we doing this? We want to use this uncertainty. And we're going to use this uncertainty to get the uncertainty in G. You can see here that if M and G are related in this way, if the gradient and G are related, then if G is uncertain, then M must be uncertain. Or conversely, if M is uncertain, then G must be uncertain. So we can use the uncertainty in M to get the uncertainty in G. How do we do that? Well, for this case, we can use this relationship, that the percentage uncertainties are equal to each other. In other words, the percentage uncertainty in G is equal to the percentage uncertainty in M. Now, I'm putting a red box around this because this is true in some conditions. It's not always true. Right now, we're just using this. However, you're going to find that in certain cases, you can do this. All right. Now, this is entirely because we've got a constant number there. 4 pi squared itself has no uncertainty associated with it. And so therefore, it has zero uncertainty itself. Okay, and that means that if we know the uncertainty, the percentage uncertainty in M, then we also know the percentage uncertainty in G. We just then need to put the numbers in. We know the values of delta M, that's the uncertainty in M. We know the value of M. We also know the value of G. We've got 4 variables, 3 knowns, 1 unknown, so we can rearrange. And we end up with an uncertainty in G, which is 0.075. One last step, we display the result of our work, which is as follows: G plus minus delta G is equal to 10.03 plus minus this 0.07. We then do a little bit more manipulation and remembering to give our uncertainty to one significant figure and then tidying up at the end here. And we've got a value of 10.03 plus minus 0.08 newtons per kilogram. A lot of work there, all right? A lot of stuff has gone into that. So what I want you to do is to try and follow the process that you've seen here to do it for your work. You're going to have to use that line ST function to find the values of the uncertainty in M. You're then going to have to relate the uncertainty in M, the percentage uncertainty in M, to the percentage uncertainty in G, and then use that to determine the uncertainty in your value of G. Thanks for watching, and I know there's going to be questions for this one, so feel free to ask them.